My name is Erik. Thanks for being here. Today I'm going to talk about how to measure or quantify the shape of plants using TDA, topological data analysis. Now, this is a very cool project that mixes a bit of math, a bit of computer science, some statistics, and a lot of plant biology. And when I say plant biology, I mean, I'm plant, a lot of plants. So for instance, when you go outside and just look at the trees, even right now, spring, at least here in Michigan, spring is finally coming. Still cold, but you can still see trees, flowers, fruits, shoots, and all these plants have beautiful internal architecture. In the lab at Michigan State University, in the basement, we have an X-ray CT scan, just like when you go to the hospital, and we put all these plants, all these parts of plants inside there, and we obtain beautiful internal structure, all the vasculature, and one thing we wonder is, how do we measure this shape? How do we extract information from these large X-ray CT scans? And to that end, we turn to TDA, topological data analysis. So the whole pipeline of TDA is like you see in this slide. On one hand, we start with some raw data, 3D scans of plants. But in general, TDA can take point clouds, can take images, can take time series, anything that you name it. And we go from the whole point is that we go from the notion of shape that can be squishy, because when you wonder about shape, then how you might ask how pointy is pointy, or how round is round, or how heart-shaped is heart-shaped. So TDA goes from that squishy term of shape into a series of numbers, as you see in the middle column. I'll explain a bit more on how do we go from shape to numbers. And the point is that once TDA helps us to convert shape to numbers, and the third column, you see that we are able to do basic statistics and machine learning with those numbers. Now, specifically when I discuss shape, my lab right now has focused on the shape of barley. You might not be aware of, but barley is one of the most, if not the most versatile and adaptable crop out there since dawn of humankind. Since humankind discovered agriculture, barley has been with us, which means that barley has expanded all over the world, as you see in the on the left bottom corner. Barley has expanded throughout the Eurasian continent, and these days we have barley that grows in Russia or Morocco, Ethiopia, all the way from Tibet to Scotland. And even if we just look at the seeds, we can see that shape has changed. Seeds in the Tibet are very small and round, and seeds in Scotland, they are larger and they are more elongated. And we wonder, how does shape actually play a role in this adaptability? Because it's definitely there. So to be more specific, our data consists of this experiment. We got this data from the cross-composite experiment too, with some collaborators at UC Riverside. It's a really cool project. They started back in the 1920s when a couple of plant biologists, Harry Harland and Mary Martini, they went all around the world, collected 28 different varieties of barley, 28 parental genotypes. And then they crossed everybody against everybody, so you have 378. Well, something happened that there are actually 379 possible hybrids. And you then let nature do nature, and they will just, each of these hybrids, it will just keep reproducing over and over again for the next 58 years. So the really cool thing of all these experiments is that we can see evolution in real time. We start with 28 parents, and they were brought to California. They saved all over again for 60 years just to see what happens, just to see which of all these possible combinations might be the best for the Californian climate. And to make things even cooler, there's a record of each of these generations, of each of these hybrids, and each year. and the seeds have been kept, and those seeds can be planted again, they can be regrown, and they can be genetically analyzed. So we have all this shape information combined with genetic information. Now, as I mentioned at the beginning, at the basement, we have this X-ray CT scan machine. So we show all the barley inside, all the panicles. We have to get a bit creative with foam trays to scan them in batches of 4. And after a lot of image processing, for instance, we were able to get 3D digital images of all the grains. So by the end of the day, we're working with more than 38,000 grains, and just looking at different generations, at the founders, then 18 years later and 58 years later, we see that barley just on its own, it's getting larger and wider. So that's a really cool experiment, just looking at how shape has changed over the years. But we can do more. And when you say shape, you can say length, width, height, surface area, volume of these grains, but how do you measure this like barley in the middle? So we turn topology, and topology is the mathematical abstract way of thinking of shape. In particular, we go with a very simple topological number known as the Euler characteristic, which can be computed as the number of vertices minus edges plus faces. For instance, if you look at the Platonic solids and you do this operation, vertices minus edges plus faces, you will always get the number 2, which is not surprising because all of the Platonic solids, pyramids, cubes, and dodecahedron, for instance, if you think of them as made out of clay, and then you pat the corners, slowly but surely, you will get a sphere. So if these were made out of clay, all of these 5 figures are spheres. And the Euler characteristic is also the number of connected components, loops, and voids. So all of these things are one thing, one connected component. They have no loops, they have no holes, and if they are hollow, then they have void inside. So that's why we always get the number 2. Now, the Euler characteristic might be too simple on its own. It cannot distinguish a sphere from a cube. Certainly, it cannot distinguish 2 seeds from one another, but we can chop the seeds, digitally speaking. So we have a digital image of the seed, and then we can chop the seed across a given direction. So let's say we chop the seed in many slices across this red axis, left to right, and then we chop it top to bottom, and then we chop it back and forth across the red, blue, and green directions. And as we keep chopping the seed, the Euler characteristic will change. And our main goal is to measure how the Euler characteristic changes as we chop the seed across different directions. This is known as the ECT, as the Euler characteristic transform. And the main reason there are reasons why we are interested in doing this. The first is that it's very easy to compute. Again, it's vertices minus edges plus faces. So even though these scans are extremely large, we can compute them in no time at all. But mathematically speaking, we can also prove that the ECT summarizes everything that there is to know about shape if we chop across all directions. Now, all directions are infinite. But as a proof of concept, we decided to go with a very finite number of directions, just 158, as you can see in this figure. We chop the seed 8 times for each of the 158 directions, so we obtain a 1200 dimensional vector, reduce dimensions with kernel PCA, and then we train an SVM. So with these shape signatures, we attempt to classify the seeds, to classify genotypes barley genotype based on shape alone. So we do it in 3 different ways, using traditional descriptors like length, volume, width of the seeds, or we can classify using topology, as I described the Euler characteristic, or we can combine both traditional and topological descriptors. And the end result is that if you use traditional or topological descriptors, the machine does roughly the same job. It classifies 55% of the time correctly, Again, there are 28 possibilities, so 55% is actually a decent classification accuracy. But if you combine, all of a sudden you go from 55 to 70% of accuracy, which means topology is actually measuring something that traditional measures are not capturing. There's some hidden information that topology is capturing. And yeah, and that will be it. And thanks for listening, and I'll be glad to questions.